This is part 8 of a series on support vector machine. In this video, we will look at multi-class classification using the one-vs-rest method. This video was produced in Korean and translated into English. My voice was generated using AI text-to-speech. In the last video, we looked at multi-class classification using the 1v1 method. We created a decision rule for OVO and implemented it in code. In this video, we will create a decision rule for OvR and implement it in code. As seen in the last video, OVO separates the two classes through the binary classification. 6 boundaries are needed to separate the 4 classes. Then, the final class of the test data was determined by majority vote using the 6 boundaries. OvR or OVA separates one class from the rest through the binary classification. If the number of classes is n, then the number of boundaries required is also n. Use all n boundaries to predict the class of the test data. Let's look at the data below. There are a total of 4 classes. Red data has class 0. Blue data has class 1. Green data has class 2. And the black data has class 3. This straight line is the decision boundary that separates the class 0 from the rest. And this straight line is the decision boundary that separates the class 3 from the rest. The W and B of these boundaries are as follows. And the equations for these boundaries are as follows. This is the equation of this boundary. W1 is positive 4.88, and W2 is negative 1.74. And the intercept B is negative 3.76. The decision functions of these boundaries are as follows. A test data point is located at 1.0, 0.7. When we input the test data into these decision functions, the outputs of y-hat are as follows. And the OvO decision rule created in the last video is like this. If the y-hat of the boundary dA, B is positive, the test data point is predicted to be class A. Otherwise, it is predicted to be class B. Let's apply this rule to the 4 boundaries of OvR. Let's use the first boundary to predict the class of this test data point. Since the y-hat is less than 0, it is classified as the rest. This means that the test data point is 4.0 away from this boundary in the rest direction. If so, that means it's not class 0. The prediction results using all boundaries in this way are as follows. The y-hat value of the second boundary is positive, so it is predicted to be class 1. This means that the test data point is 3.31 away from the D1, rest boundary towards class 1. The boundary with the highest y-hat value can be used to predict the class. Therefore, we predict that the class of this test data point will ultimately be 1. There can be multiple boundaries with positive y-hat values. In this case as well, you can just use the boundary with the highest y-hat value. This is because the test data point is furthest from that boundary. The further the test data point is from this boundary, the more confidently it can be predicted to be class 1. Then we can finally create a simple decision rule for OvR as follows. Classify the test data using the boundary with the highest decision function value. Now let's look at the test data point 2, located at 0.5, 0.1. When we input this test data point into the decision functions, the outputs of y hat are as follows. All y hat values are negative. This is because the test data point is in a blind spot. The y hat value of the dia1, rest boundary is the largest. This means that the class is not 1, but because the test data is closest to this boundary, it is least likely not to be class 1. It makes sense to classify this data point as class 1. Therefore, the rule below can be applied in this case as well. Next, let's implement multiclass classification using the OvR method. Scikit-learn's SVC performs OVO internally, so we will use 1V's REST classifier for OvR. We'll look more at SVC and OvR in a moment. The data we will use is like this. As used in the previous video, it consists of 4 classes. Create an 1V's REST classifier model. We use the linear SVC as the base model. We can also create a nonlinear SVC model using RBF or polynomial kernels. Fit this model to the training data. This model has 4 base models as shown below. This is because the number of classes in the training data is 4. W and B for each base model are as follows. These are the parameters for the 4 boundaries. Visualize the data points and 4 boundaries. The equation of a decision boundary looks like this. Isolating x2 gives us the equation of a straight line as follows. In this figure, here we have the x1 axis, and here we have the x2 axis. Using W and B obtained on the left and the sequence data x1, we find x2 using this formula, and we plot this straight line. Then 4 boundaries will be drawn like this. Next, let's predict the classes of the test data. To visually check the decision boundaries, we randomly generate 2,000 test data points. We then predict the classes of this test data. Let's call the predicted classes ypred1. If you have made it this far, the OvR multiclass classification is complete. However, here we will manually implement the predict function of this model to better understand how OvR works. The decision function for the test data can be calculated using this formula. For a linear SVC model, W is available, so we can compute the decision function directly as follows. For the nonlinear SVC model, W is not available, so we use the decision function provided by this model. The decision function values of the test data are as follows. DF is a matrix with 2,000 rows and 4 columns. The first row contains the decision function values for the first test data point. These are the y-hat values calculated using 4 decision functions. The first column contains the y-hat values using the boundary between the class 0 and the rest. The second column is for the class 1 and the rest, and the third column is for the class 2 and the rest. And the fourth column is for the class 3 and the rest. This y-hat value is the largest, so the first test data point is classified as class 1. The second test data point is classified as class 3. In this way, all 2,000 test data points can be classified. This is the decision rule for OvR. Let's call the classes of the test data predicted this way ypred2. Let's check whether ypred1 and ypred2 match well. Finally, let's visualize the test data and the predicted classes. The results are as follows. The ypred1 and ypred2 are exactly the same. The training data points and 4 boundaries look like this. And the final decision boundaries found through 2,000 test data points look like this. You can see that the 4 classes are well separated. Let's run this code. The results are as follows. You can see the 4 boundaries like this. Next, let's use the SVC model. Let's take a look at scikit-learn's SVC documentation. You can specify OVO or OVR in the decision function shape argument. Even if OVR is specified in this argument, SVC will perform OVO internally. Then, the OVO results are used to construct the decision function values in the form of OVR. Create SVC model. We set the kernel argument to linear. This argument can also be set to RBF or polynomial to create a nonlinear SVC model. And specify the decision function shape argument as OVR. Fit this model to the training data. Let's check W and B of this model. The results are as follows. W is a matrix with 6 rows and 2 columns, and B is a vector with 6 elements. This is the same format as the output from OVO seen in the previous video. In other words, these are the parameters for the 6 boundaries. Even if you specify the decision function shape argument as OVR, you can see that SVC performs an OVO internally. Next, let's check the decision function values of the test data. The results are as follows. DF2 is a matrix with 2,000 rows and 4 columns. These are the y-hat values for the 4 boundaries. This is the same format as the DF we got from the code on the previous page. SVC uses the OO matrix to generate an OVR matrix. I haven't figured out how SVC creates the OVR matrix. This value is largest in the first row. Therefore, the class of the first test data point is predicted to be 1. The remaining test data points can also be predicted this way. And the final decision boundaries for 2,000 test data points look like this. You can see that the 4 classes are well separated. Let's run this part as well. The results are as follows. So far, we have implemented multi-class classification in SVM using the OvR method. In the next video, we will look at the regression using support vector.